This video covers limits. We will be looking at limits numerically, graphically, and analytically. The first way we're going to look at a limit is the graphical approach. Graphically, we say the limit exists if both pieces of the graph, approaching from the left and approaching from the right, those two pieces must go to the same value. An example of this would be, suppose we draw a graph. And at that graph, we have this value x equals c. And we're going to put a dot here, and we're going to draw just a simple line graph. And we'll draw another piece that looks like this. So this the y value here is f of c. Now, if we try to do this, the limit as x approaches c with a negative, this is going to mean from the left. So we would look at the part of the graph where x is less than c. So we take this piece of the graph and we end up actually at the value f of c. So if we tried to do the same thing and we took the limit as x approaches c with a plus sign, which is going to mean from the right, then we end up with some undefined value. You know what? We could actually attach a value to this. Say this was, we'll call it 6. So then the limit as we approach c from the left, from the right, would be 6. You know what? We could actually call f of c a specific value. You won't need that. We'll call this 1. So instead of putting f of c, we'll just make this 1. So in order for the limit to exist, both pieces of this graph have to be going to the same value. So we can see the limit doesn't exist because in one case, we end up with 1. And when we're approaching from the right, we end up with 6. So the limit value has to be one number. So both of these need to either go to 1 or both need to go to 6. But since they go to two different values, we would say the limit here does not exist. You know what? I'll make a complete sentence. Limit does not exist. An example where we could have the limit existing, but the function value is not defined there is, imagine we draw another graph. So we'll call this value, we'll still call it c. We'll call this value 1, and we'll put an open circle. We'll draw the right part of the graph, and we'll draw the left part of the graph. So when we approach c from the left, the limit value is 1. So we have the limit as x approaches c from the left for f of x is equal to 1. And the limit as x approaches c from the right for f of x is also equal to 1. So because the left limit and the right limit exist and they're the same value, we have the limit as x just approaches c, no sign, for f of x is equal to 1. So this could also work if the function was defined here. If we filled in this circle, we still end up with the limit of 1. So the only time that the limit doesn't exist is basically if we have a skip in the graph, which means that we have some type of discontinuity. So what we're going to do is look at the notes that we completed in class and just go back through those for people who need that. So we're going to start with the second example. So in class we did the limit as x approached -2 for f of x. We found out that the limit did not exist. And that's because the limit as you approach x, x equals -2 from the left ends up at 2. And the limit as we approach -2 from the right using this other part of the graph ends at -1. And so 2 and -1 are not equal. So we have a limit that does not exist. when we find the limit as x approaches 0, if we use the left part of the graph, we end up with 1 as a limit value. And if we approach from the right, we also have 1 as a limit value. So in this case, the left and the right limit agree, so our limit is 1. And also note that f of x is defined at x equals 1, but that's not a prerequisite for the limit to exist. So for example, 3, we have the limit as x approaches 3 from the left, that's 0. The limit as x approaches 3 from the right is also 0. And so the limit as x approaches 3 is 0. Now notice that f of x is not defined at x equals 3, but again, that's not a prerequisite for the limit to exist. So we're going to go back to do example 1. I would encourage you to put this into your this function into your TI or Casio if you're using one. Let's go through some calculator tricks quickly in case you don't know some stuff. So let me set this back to +1. It's going to change. So first we go to y equals and we put in x squared minus 4 divided by x squared minus 5x plus 6. So a handy shortcut is if you press the alpha key and you press y equals, you get a fraction instead. And so we can put in the same function where we have x squared minus 4 over x squared minus 5x plus 6. And we're going to go back to the same table. So we press second and we press graph to pull up our table. So right now, it's giving us an error at 2 and 3. And for this example, we're trying to approximate the limit when x approaches 2. So now if we want to narrow in, we want to have 1.5, 1.75, 1.9, 1.99. So a way to do this using your calculator is we press the plus key, and that allows us to change how much x increases by. So initially we'll just do 0.1. And so we end up with 1, 1.1, and so forth. So when x is 1.5, we have a value of negative 2.333. We can also fill in 1.9. That's negative 3.545. We can probably do 2.1 as well. We'll just jump around. So at 2.1 is negative 4.556. Negative 4.556. And when x is 2.5, we have negative 9. And so if we go back and fill in 1.75, we can do plus 0.05. And then we have when x is 1.75, we get negative 3. And when x is 2.25, negative 5.667. And then if we go to 2 and we do plus 0.01, excuse me, take that out. We have at 1.99, it's negative 3.95. And when x is 2.01, it's negative 4.051. So negative 4.051. So it seems that as x approaches 2 from the left using values smaller than 2, the y value seems to be approaching negative 4. And the limit as x approaches 2 from the right, meaning we get closer and closer to 2, but using values greater than, the y value also seems to be approaching negative 4. So we're going to write that limit as negative 4. We'll come back to that when we talk about analytic methods. So for analytic methods of finding the limit, the easiest way to find the limit is to substitute in the value and see what happens. So imagine for a moment we had, instead of 4, which is going to give us a discontinuity, we try to substitute in 1 instead. And we'll just keep track of that over here. So we're going to have this same function where we have the limit as x approaches 1 of x squared minus 4 over x squared plus 2x minus 8. So if we substitute in 1, we're just going to have 1 squared minus 4 over 1 squared plus 2 times 1 minus 8, which 1 minus 4 is negative 3. And on the bottom, we get 1 plus 2 is 3 minus 8 is negative 5. So that limit is 3/5. So the easiest way to find the limit is to substitute in the value. Now the problem comes with, what if we have to do something different where we get 0 over 0? So if we look at this example, we have the limit as x approaches 4. And so if we substitute in 4, we'll get, I can write this over here instead. We'd end up with 16 minus 4 over 16 plus 2 times 4 is 8 minus 8. So we end up with 12 over 0. So the problem here is that we end up with a 0 on the bottom. So the thing that we check is, can we factor this equation? So it does factor, and we would get, I will write this here, we'll have the limit as x approaches 4. And so on the top, we have a difference of perfect squares, which is x plus 2 times x minus 2. And on the bottom, what multiplies to be negative 8 and adds to be positive 2, that's going to be x plus 4 times x minus 2. So we can cancel out our x minus 2's. We end up with x plus 2 over x plus 4. And so now we have the limit as x approaches 4 of just x plus 2 over x plus 4. And if we substitute in 4, we end up with 6 over 8, which reduces to be 3/4. So sometimes we have to factor and cancel, and on the back, we'll see some other examples of what we have to do. So in this case, for the next example, we have x squared plus 2x minus 15 divided by 2x squared minus 5x minus 3. So we can just assume, I'm sorry, this was out of view. So we have x squared plus 2x minus 15 over 2x squared minus 5x minus 3. So if we quickly check, if we substitute in 3 on the top, we'd end up with 9 plus 6, which is 15, minus 15, which is 0. And on the bottom, we'd have 3 squared, which is 9, times 2 is 18, minus 15 is 3, minus 3 more is 0. So we end up with 0 over 0. When that happens, it probably means that there's a factor that's common between the two things that we can factor out. So to find the limit, we want to do the limit as x approaches 3 of, we can factor the top to be x plus, let's see, x plus 5 times x minus 3 over. So then on the bottom, we'll talk more about factoring in class, but 2 is a prime number. So the only thing that multiplies to be 2x squared are a 2x and an x. So the question is, how do we get a negative 5 using factors of 3? So if we put a 3 here and a 1 here, that will give us a 6x minus an x, or 6x and an x. And so we make this 3 and we make this 1. So if we want the 5 to be negative, we should make the larger factor negative. So negative 3 times 2x is going to be negative 6x, and a positive 1 times x is going to be 1x. So negative 6x plus 1x is negative 5x. Our x minus 3's cancel, and we get the limit as x approaches 3 of just x plus 5 over 2x plus 1. And now if we substitute in 3, we end up with 8 over 7. So what we did here was we factored, canceled out the common factor, then replaced the limit value, and we ended up with 8/7. Notice that in each step, I kept the limit until I did the limit. It's just technically correct to do so. For the next example, we have x plus 2 divided by 2 minus the square root of x plus 6. If we substitute in negative 2, we'd end up with 0 over 2 minus, so negative 2 plus 6 is 4. The square root of 4 is 2. So 2 minus 2 is 0. When we have a square root on the bottom, the thing that we generally want to do is multiply by the conjugate. So we're going to have x plus 2 over 2 minus the square root of x plus 6. And then we're going to multiply by the conjugate, which means that we just change the sign that's down here and multiply it by that in the numerator and denominator. So we're going to have 2 plus the square root of x plus 6 in the numerator and divided by 2 plus the square root of x plus 6 in the denominator. So on the top, what we're going to have is, we'll just leave this the same. We'll have the limit as x approaches negative 2. We'll just leave it as x plus 2 times 2 plus the square root of x plus 6. And then on the bottom, we're going to have 2 times 2 is 4. And then, all right, because it's a difference of squares, the 2 times the positive square root of x plus 6 and 2 times the negative square root of x plus 6, they cancel. And then we have negative square root of x plus 6 times the square root of x plus 6, which gives us minus just x plus 6. And that reduces to be, we'll write this here, the limit as x approaches negative 2 of x plus 2 times 2 plus the square root of x plus 6. And 4 minus x minus 6 is going to be negative x minus 2. So we're going to have on the bottom negative x minus 2. So this is the same as having instead negative x plus 2. So we don't need that. So x plus 2 divided by negative x plus 2 is going to give us the limit as x approaches negative 2 of, now these cancel out to make a negative 1, so we just have negative times 2 plus the square root of x plus 6. And now we can substitute in negative 2, and that gives us negative 2 plus 6 is 4, the square root of 4 is 2, plus 2 is 4 times a negative is negative 4. So in this example, we multiply by the conjugate. We did not multiply out the top. On the bottom, we conveniently ended up with something that allowed us to cancel the x plus 2 that we started with. For the next example, we have a piecewise function. We have x squared minus 1 if x is less than or equal to 0. We're going to use the function x minus 1 if x is between 0 and 2. And we're going to use x minus 3 if x is greater than or equal to 2. So the only points that could be a problem are these endpoint values. So for the first example, we're trying to find the limit as x approaches negative 1. And so since negative 1 is strictly less than 0, we're just going to use this function. So we're going to have negative 1 squared minus 1, which equals 0. So the limit when x approaches negative 1 for f of x, that's just 0 because we used this function. For the next one, we are finding the limit as x approaches 0 for f of x. If x approach, so now we have a problem because we have two functions that contain x equals 0. We have this one and we have the x minus 1. So that means that we have a left limit and a right limit. The limit as x approaches 0 from the left for f of x is equal to, we substitute 0 into this, we get negative 1, and the limit as x approaches 0 from the right for f of x is also equal to negative 1 because 0 minus 1 is negative 1. So the limit as x approaches 0 in general is negative 1 because the left limit and the right limit are the same thing. When we look at x equals 2, we have another case where 2 is the right endpoint for this function and the left endpoint for the third function. So we again need to find, we'll draw a line, we need to find the limit as x approaches 2 from the left for f of x that equals 2 minus 1, which is 1. And then the limit as x approaches 2 from the right for f of x is equal to 2 minus 3, which is negative 1. So because 1 and negative 1 are not the same, this limit does not exist. And finally, for x being greater than 6, because 6 is greater than 2, we're just going to use the bottom function. So 6 minus 3 is 3, so that limit is 3. The last thing I want to do in this video is cover quickly one-sided limits. Now, we've already done this for the previous example and the examples on the front. So a one-sided limit, as we already know, is given by a direction where if it's a positive, it means approach from the right. If it is a negative, it means approach from the left. So for this graph to the right, we are first finding the limit as x approaches 0 from the right for f of x. Now, if we follow along in this graph, that's going to give us 0. If we approach 0 from the left, we're going to have a limit value of, that seems like negative 2.5. So we'll put negative 2.5. And so then the limit as x approaches 0 does not exist because the left and the right limit are not the same. All right, that concludes a somewhat lengthy video over limits. If you have questions, please talk to me in class.